Let's look at section 10.6, conservation of energy. Let's specifically look at work is equal to the change in energy, where the change in energy is the change in kinetic energy plus the change in potential energy plus the change in thermal energy plus the change in nuclear energy plus the change in whatever energy else you can think of. If we have an isolated system, then work is equal to 0. If work is equal to 0, then the change in energy is equal to 0. In other words, final energy is equal to the initial energy. Or we can break down our total energy, E, into kinetic energy final plus potential energy final plus thermal energy final plus ... And that's equal to kinetic energy initial plus potential energy initial plus thermal energy initial plus ... If you have an isolated system in our conservation of energy, this is where you're going to spend most of your time, writing equations like this. Let's look at an example. A spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. So let's write our given. We have VA equal to 2 meters per second. If the spring is compressed twice as far, so in this case, our spring is compressed at a distance XA. And we're going to now compress it at XB, which is equal to twice XA. And we want to find the launch speed. So that would be VB. So let's take a look at this. Our equation is going to be conservation of energy. We have an isolated system. We just have a spring and a gun, and that's shooting a ball out with a speed V. And the spring is compressed some distance x. So here's our division line, and this would be the before case, or the initial case, and this side would be the final case. We have a conservation of energy, so we want to know what's all being worked on, or what's all the energies in our total energy in the initial case. Well, is there any kinetic energy? Is there any potential energy? Is there any thermal energy in the initial case? And the answer is yes. We compress the spring by a distance x, so we have potential energy by spring in our before case, or the initial side. That's the only thing we've got. We compress the spring by an amount, and then what happens is the spring totally uncompresses, and in our final case, we transfer all that energy into kinetic energy. So let's take a look at case A. Case A. We have got 1/2 kx squared initially. K is just a spring constant. You look it up in a table. So this is A. It's compressed XA squared. And once we release it, we get a speed of 1/2 m, mass of the ball, and our V squared, our V is 2 meters per second. And we need to square it. So we solve for XA, or we just leave it this way. We have kx squared, our halves drop out. We get kxa on the left-hand side squared, and that's equal to 2 squared is 4 meters squared per second squared times m. Now let's look at case B. In case B, we still have the spring being compressed, 1/2 K. It's still our spring constant K, but now we're compressing it to XA. So we have 2XA This is our XB here. And we need to square it. And that is going to be equal to 1/2 mv squared. 1/2 m and vb squared. Once again, our halves drop out. And we have a k here. 2 squared is 4 xa. And that's equal to mvb squared. So we're going to call this equation over on the right equation 1. We're going to call this equation on the left equation 2. And we're going to divide equation 1 by equation 2. So let's take equation 1 and divide it by equation 2 so we can ratio and get rid of some of our values. So here's equation 1. We've got k times xa squared and that's equal to 4 meters squared per second squared times m. Now we want to divide that by equation 2, which is k, 4, k, xa, oh, that one's a squared, 4xa squared and then on the other side we have an mvb squared. So here's our m and here's our vb squared. Now we can get rid of things. The mass doesn't matter, it divides out. The amount of xa compressing doesn't matter, it divides out. The spring constant divides out. We want to solve for vb squared. So we get vb squared is equal to 4 times 4 is 16 meters squared per second squared. We take the square root of both sides of the equation and solve, and we get VB, which is the speed, is equal to 4 meters per second. So the answer must be D. Let's take a look at a second example. Quinn is at rest at the top of a playground slide. The main part of the slide is 5 meters long, and it is tipped at an angle of 30 degrees. Therefore, we can solve for the height h by using the sine of the angles opposite over the hypotenuse, and that's 2.5 meters. So the height is 2.5 meters. Quinn starts sliding, moving down from the tipped section, and then the slide levels out so that he leaves the slide at 2 meters per second. Moving horizontally. If Quinn's mass is 24 kilograms, how much thermal energy is deposited in his trousers and in the slide? So let's take a look at the before case and then the after case. We have a conservation of energy. Here is our system. We draw a circle around our system. No heat is being transferred in. We're not talking about adding any heat or taking any heat away. We're not doing any work on the system. So therefore, we have an isolated system. Since we have an isolated system, we have the energy, total energy before, must equal the total energy after. Now we have to decide the types of energy that we have. So we know we're going to start out with our equation equal here. Quinn is at rest at the top of a playground slide. So Quinn's up here at rest, but Quinn has a height h. Therefore, we know we have gravitational potential energy on our before side. This is our before case. Since Quinn is at rest, there is no speed, there is no kinetic energy. We don't have any springs here, so there's no spring potential energy. We don't have any thermal energy, because thermal energy, you need to have some kind of friction here. We don't have any here, because the Quinn is just sitting here. So therefore, we have nothing else in the before case. We don't have any nuclear, we don't have anything else. The only thing we have is gravitational potential energy. That's the only thing we have before. So I can set this now equal to our after case. Let's take a look and see what decides of energies that we have in our after case. The after case, well, let's put our before case. Here's our before is up here at the top, and our after case is down here at the bottom. Well, at the after case, we have no more potential energy because we're down at the ground, but we do have kinetic energy because Quinn is sliding to the right. So we do have kinetic energy. And we also have thermal energy from friction sliding on her pants or his pants on the slide. So we have E thermal. So this is our equation. We set up our equation. Let's take a look at our given. Our given, we have potential energy initial due to gravity, and that is equal to mgh. We also have mass equal to 24 kilograms, and we have a V final speed. V initial is equal to 0. That's where our kinetic energy comes to 0. And our final speed is equal to 2 meters per second. Our goal here is to find our E thermal. So we need to set up our equation, which we did, and now we need to solve it. Our potential energy initial is mass times gravity times height, and that's got to be equal to the kinetic energy, 1/2 mv squared, plus E thermal energy. So we need to solve for E thermal. E thermal is equal to mgh. The mass is 24 kilograms. Times gravity, which I'll just put here as g, times the height, which is 2.5 meters. You need to subtract off 1/2 mv squared. Our same mass of 24 kilograms. Times v squared. Our speed is 2 meters per second. And if we do all that math, we're going to get a value of 588 joules minus 48 joules, which is 540 joules. If we do the math, our E thermal that we solve for is 540 joules. The active coin sliding down the hill transfers 540 joules of thermal energy from the friction of the pants on the slide. So these are examples of how you solve for conservation of energy.